Buenas tardes a todos. Vamos a empezar con el seminario de hoy, que será impartido por el doctor Felix Mirabel. El doctor Mirabel es el director de investigaciones del CEA en Francia, el director de la ESO en Chile. Tiene un doctorado honoris causa por la Universidad de Barcelona y ha recibido muchos premios por su investigación. Por ejemplo, el premio Rossi de la American Astronomical Society, el premio de física de la CEA en Francia y el premio de la Academia Nacional de las Ciencias de 2010 en Argentina. Sus líneas de investigación principales son los agujeros negros, las galaxias y la estructura de nuestra galaxia. Y el seminario de hoy es sobre agujeros negros.
Muchas gracias. Creo que sí, ¿no? ¿Me escuchan bien? Bueno, es un placer volver a estar aquí después de mucho tiempo. Y uno de los objetivos de esta visita ha sido ver las condiciones de infraestructura que habría aquí en Tenerife para la instalación del futuro Cherenkov Telescope Array, la versión norte, que me han pedido que yo coordine todos los aspectos de los estudios de lo que hace a la infraestructura para los posibles sitios, ¿no? Ahora, la charla de hoy va a ser una charla un poco de review. Perhaps I have to switch to English, right? Yes, I'm sorry. And, I always wanted to, when I went into astronomy, I wanted to do cosmology, but at that time, cosmology was, I would say, pure speculation. And now it's becoming a very well-funded science. So I try to learn about cosmology using the research that I have been done on stellar mass black holes. And the idea is to talk about what might have been the role of stellar black holes at the dawn of the universe, in the very early epochs of the evolution of the universe. And one of the problems that is a problem that is not solved is how the universe have been reionized. As you know, there was after the Big Bang, after 400,000 years after the Big Bang, until the first billion years, the universe was mostly opaque because the intergalactic medium became neutral. So, and this is very well known, and as you know, the Gunn-Peterson effect that can be seen by the absorption. So, during this epoch, a large epoch, we don't know how the universe became transparent again. And the current idea is that stars, massive stars, the first stars, produce ultraviolet radiation that progressively ionize the intergalactic medium and becoming it transparent again. And actually, today it has been published, an article in Nature, where it is proposed that stars did all the work. And what I'm going to show you is that very likely stellar mass black holes, namely the fossils of massive stars, also play an important role in the process of reheating and reionizing the intergalactic medium. So the question is, what might have been the role of stellar mass black holes in this process of turning the universe again transparent? And the plan of the talk I mean, to justify why I think stellar mass black holes should have play an important role. For that, I will review first the predictions from theoretical models on the formation of stellar mass black holes by implosion, namely the models, the current models for stellar evolution of massive stars. And secondly, I will review some of the observations of compact objects, namely neutron stars and black holes, that are consistent with the idea that black holes might form by implosion directly. And then I will show the evidences that the formation of black hole binaries depends on the star formation rate and the metallicity of the host galaxy. And then I will go on the cosmological implications. Now, let me remind you the current models for the evolution and the end of massive stars. This is a famous diagram for how what will be the destiny of massive stars, where it is plotted here on this axis the metallicity, and on this axis the mass of the progenitor star. And this model has been developed for massive stars without rotation. And the prediction, as you can see, this is solar metallicity, is very difficult to form black holes from progenitors that have solar metallicity or larger, simply because the star produces, because of the metallicity, strong winds, loses mass, and the core that will collapse will not be massive enough to form a black hole and will form mostly neutron stars. And but for metallicities that are below half solar, there is the possibility of forming black holes by direct collapse. Namely, if the star doesn't lose much mass due to stellar winds, which depend on the metallicity of the progenitor, then the core that will collapse might be massive enough to collapse into a black hole. And so for masses greater than 40 solar masses of the progenitor stars and metallicities below 1/5 solar, according to this model, one can form black holes directly by implosion. Namely, there is no explosion of supernovae. Namely, there is what I would call implosion. And this is another model developed by now incorporating rotation of the progenitor star, developed by the Geneva group. And you see that also incorporating rotation, which implies mixing of the chemistry components of the layers, also one can form black holes directly for a very low metallicity of the progenitors, namely for stars with masses greater than 30 solar masses and metallicities that are less than 1% solar. These stars collapse directly into black holes. There are some caveats because the destiny of massive stars, besides depending on the rotation of the progenitor, also depends on the magnetism and binarity. But without going too far, on this subject, in fact, models that incorporate binarity reach the same conclusions, basically. So the idea is that according to the current models, low metal progenitors may form black holes directly by implosion. And so if this is correct, then from these theoretical models, one infers that the mass of the stellar black hole, the fraction of black holes over neutron stars, and the fraction of binary over solitary black holes should increase with the star formation rate of the host galaxy and the decreasing metallicity of the progenitors. Namely, why the binaries, if half the massive stars are formed in binary systems, and one of these massive stars collapse into a black hole directly without ejection of matter, the black hole and the companion star will remain gravitationally bound. There is no destruction of the binarity of the system. And this is a very important fact. Namely, if one forms directly, one has a binary composed of two very massive stars, and one of the stars goes directly to form a black hole, the system will remain gravitationally bound. What unbounds the system is the explosion of a supernova. And so, silence, still, I don't know what this means. Should I shut up? And, algún botón aquí. Okay. So the fraction of black hole high mass X-ray binaries should increase the star formation rate of the host galaxies and decreasing metallicity of the progenitors. This is a consequence of the models. Now, can we test in some way this hypothesis? So I'm getting confused here. So are stellar black holes actually formed by implosion? Well, one can has to see, to test observationally this, from the properties of the fossils of massive stars, we can infer whether they finish with energetic supernovae or silently. It's the same approach that have archaeologists, that to see whether the fossils, human fossils, died violently or silently, quietly. They can go and see, and we can do the same with black holes, and see whether black holes finish through, the progenitor stars exploded before forming the black hole or not, or they went directly and collapsed to form a black hole. This is what we could call a sort of a stellar forensic approach. And there are some recent results, and this is a diagram published by Crowther et al. That synthesize the relation between the metallicity and the mass determined dynamically of black holes, and as you can see, that the mass of the black holes in high mass X-ray binaries seems to be a decreasing function of metallicity. The sample is not very large, but you see that this is metallicity, and this is the mass of the black hole, and systems, small systems with low metallicity as IC10, NGC 300, and M33 host black holes with masses greater than 15 solar masses, and we don't know, neither in our galaxy or in Andromeda, which are very large galaxies, any black hole with a mass greater than 15 solar masses. So This is a first indication that the low metallicity environments favor the formation of black holes with larger masses, because, well, there is less loose mass by stellar winds. Now, another observational results are indicating also that the occurrence rate of ultraluminous X-ray sources per unit galaxy mass in starburst galaxies is a decreasing function of the metallicity of those galaxies. And you know, ultraluminous X-ray sources, most of them are believed to be black holes with masses of several tens of solar masses accreting from high-mass stellar companion. Yes? Yeah. Here you see the antenna galaxies, and you will see here in this region what is the distribution of compact X-ray sources, and most of these compact sources are ultraluminous X-ray sources, and they are called ultraluminous because they radiate in the X-rays super Eddington flux, namely for a black hole of 10 solar masses. The radiation of 10 to the 40 ergs per second in the X-rays is super Eddington. So these are believed to be most high mass stellar mass black holes accreting from high mass companion stars. And another example, there are several examples now, is the case of the Cartwheel galaxy that we know is a very low metallicity galaxy, and you can see here the formation of ultraluminous X-ray sources in one of the rims, and the overall X-ray radiation in this very small galaxy is of the order of 10 to the 42 ergs per second. So it starts to rival the X-ray radiation of AGNs. So on the contrary, there are observations that show that high metallicity progenitors do not end as black holes. They end as neutron stars. And the cases, the clear cases we have so far is the study of the soft gamma ray repeaters, and that we know they are young neutron stars, recently formed neutron stars, and it is found that they are hosted by clusters of massive stars. These are three examples where these clusters of massive stars contain stars with masses greater than 40 solar masses in these two cases. And if one assumes that the massive star formation was coeval, so the progenitors of these neutron stars should have had masses greater than 40 solar masses, and these three sources we know are in the interior part of the galaxy, these clusters, where the metallicities are relatively high, are higher than solar. So the progenitors of these neutron stars, since they have a high metallicity, they lost a high rate of mass due to stellar winds, and the core was not enough to form a black hole and form a neutron star. So massive stars of high and as neutron stars rather than as black holes. Now, there are other indications also using and this is an approach I have carried out, is to use the kinematics of microquasars, which implies that black holes may form with or with no energetic supernovae. And that depends on each case. And you see the typical scheme of evolution of a binary system. One of the stars evolve, and the system is immersed in a common envelope phase. Then the envelope is ejected, and if one of the stars explodes, not silently, but very energetically, and the system manages to remain, despite the explosion, gravitationally bound, the center of mass will gain linear momentum, and the system should be ejected from its natal place. So, studying the kinematics of black hole binaries in our galaxy, one can infer whether that particular black hole was formed directly or through a supernova. And so far, it has been determined the space velocity, namely the kinematics of 5 black holes, X-ray binaries in our galaxy, where the black holes have masses in the range in between 5 and 14 solar masses. And to approach this, what we use are what are called the compact jets, which can be used to follow the motion of the systems in the sky. And both the steady jets and the transient jets always have compact jets, and one can determine the position of this compact jet with these compact jets using VLBI with sub-milli-arc-second precision. So one can follow during months and years which is the motion on the plane of the sky of the binary system. And then using, we are interested in the space velocity, so we need also the radial velocity of the center of mass of the system, and we need the distance to the system in order to determine the space velocity in 3 dimensions. And this has been done for different systems. This is one of the 2 cases where we found runaway black holes, namely black holes that obviously were ejected from the birthplace. And this is the first black hole found in the galactic halo at a galactic latitude of about 70 degrees, where we believe there should be millions of black holes swirling around, but we don't see. This is the first one because it's in a binary system, and this is why we could identify it through the X-rays. Now, this is a simulation, how it will move this black hole binary relative to the motion of the sun about the galactic center during a period that corresponds to the full revolution of the sun about the galactic center of 230 million years. And as you can see, this object moves as some globular clusters move, and while the general consensus now is that this object was catapulted from the galactic plane by a supernova explosion, and the binary system managed to remain gravitationally bound. And there is another system that is the second superluminal source in our galaxy that has a peculiar velocity of more than 100 kilometers per second relative to its environment. And these 2 black holes have masses, relatively small masses, in the range in between 5 and 7 solar masses. So these black holes very likely were formed through a neutron star phase. So they were formed through a mechanism called delay collapse. So first you form the neutron star, and then part of the mass ejected by the supernova will fall back and form a black hole. Now, there are other cases like the famous Cygnus X1, where here is, we know that the peculiar velocity, on the contrary here, this is a very stringent limit, is less than 9 kilometers per second relative to the parent association of massive stars. You can see here the mean motion of the parent association of massive stars, which are indicated here in yellow, and this is the mean motion on the plane of the sky. And you can see how it's moving. Cygnus X1 is moving along with the parent association of massive stars, namely Cygnus X1 remain anchored in its birthplace, and which implies that the formation of the black hole could not have been through a very energetic supernova. That very likely was mostly directly formed. And there are two other systems, GRS 1915 and this source B446, which have peculiar velocities of this range, but the component perpendicular to the galactic plane are virtually zero. For instance, in this case is 0 kilometers, and in this case 7 kilometers per second. And the point is that the velocity of these two systems is on the galactic plane, most of the peculiar velocity on the galactic plane towards the galactic center. And this component of the velocity is at least 10 times the component of the velocity perpendicular to the galactic plane. And if they would have gained these peculiar velocities by a supernova explosion during the formation, there is no reason to have such a low component perpendicular to the galactic plane. We know from neutron stars that they are moving. There is no preferential direction in the galaxy. So my hypothesis is that these peculiar velocities were gained by the very well-known phenomenon of galactic diffusion on the plane of the galaxy. And these are very old black holes. These are low-mass black hole binaries. And very likely they were formed with, if there was a supernova, with a very weak supernova. And these two black holes have masses greater than 10 solar masses. So the sample of objects is very small, but black holes with masses greater than 10 solar masses, apparently they do not show evidence for a natal supernova, whereas black holes with smaller masses, they do show some evidence for a natal supernova. Now, of course, this line of research will be greatly enhanced with the launch of Gaia, because we will be able to determine the distances and the proper motions with unprecedented precision, which is one of the critical aspects of this approach. Now, these black holes, high-mass binaries, produce, as you know, very powerful jets, and you can see here the jets produced by Cygnus. And then recently in Nature also it was reported in this galaxy the existence of a very powerful microquasar that is very likely a black hole with a high mass donor star. And also these jets has been seen now in the X-rays using Chandra. We can follow using Chandra the motion of these jets on the plane of the sky. So the energy, and one of the bottom lines of these studies is that the energy injected in photons and high-energy particles by black holes, high-mass X-ray binary microquasars may be several orders of magnitude larger than that of a core collapse supernova. This is, to produce these bubbles, the injection of energy must be enormous, at least 100 times more than a typical core collapse supernova. Now, the other area of where this is the one on studies of gamma ray bursts, and you know, these are the most energetic explosions in the universe, and they have been now seen up to redshifts of 8.2, namely deep inside the end phases of the dark ages. And we, from studies, well, with the VLT by my student, my former student, Émeric Lefloc, and that were confirmed using Hubble, that the host galaxies of long gamma ray bursts that we believe mark the formation of stellar mass black holes, the host galaxies are small irregular galaxies of relative low metallicity. And here you see the images. These are very small galaxies in general. And recent results also confirm this, that usually for a given mass of the galaxies that host gamma ray bursts are galaxies with low metal content. And this is from all sides of observational astrophysics, this hypothesis, I mean, it's been confirmed, the predictions of the theoretical models of the end of massive stars. And more recently also, there have been using a study of long gamma ray bursts. It is found that long gamma ray bursts are enhanced, are produced with enhanced rates at redshifts greater than 3 than expected from star formation measurements. The star formation measurements, the last ones are this, and this is the rate of long gamma ray burst production. This is from data from SWIFT. So, and there are other observations that confirm this trend. So, because massive stars with low metallicity end as black holes by direct collapse, the cosmic evolution of metallicity must imply a cosmic evolution of black holes, high mass X-ray binaries. So this is a conclusion from theoretical models and from observations. This should be the case. Namely, the mass of stellar black holes, the fraction of black holes over neutron stars, and the fraction of binary over solitary black holes should increase with redshift. So, and if one goes to the very early epochs of formation of stars at very high redshifts, one will say that the fraction of black hole binaries must have been enormous. And So what may be then the cosmological implications of these X-ray binaries during the dark ages? Could the neutral phase, namely during the cold neutral phase of the intergalactic medium that lasted from 400,000 years up to the first billion years after the Big Bang. And this question was formulated by Sunayev in the 7 microquasar workshop, and now it has become, which took place 2 years ago, but now it has become a very, very timely question. And the reason is that the latest computer simulations of formation of population-free stars indicate that they were not, as believed before, very massive stars with masses of 500 solar masses, but multiple systems dominated by binaries with masses in the range of 10 to 100 solar masses. And there were, in the last year, 3 papers by 3 independent groups that, using more power, more computing power, arrived to this conclusion. And if that is the case, then one should form a very large quantity of these objects. And while there are some, also on the other hand, the identification of a gamma ray burst at a redshift of 8.2, that in fact it has properties that are comparable to the long gamma ray burst observed at lower redshifts. And also there are now galaxies being observed with the new infrared camera installed on Hubble up to redshifts of 8 and something. There is a recent paper that appeared in Nature 3 weeks ago, I think. So during the dark ages, we are starting to penetrate into the dark ages to probe how the universe was heated and reionized again. So the question is that I formulate is what may have been the consequences of feedback from this very large population of black hole high mass X-ray binaries during that epoch. And for that, well, I look for collaborators that work on cosmology from Harvard, Avi Loeb, Dijkstra, and Pritchard, and we have compared the ionizing power of microquasars versus the ionizing power of massive star progenitors of these microquasars. And this is the number, counting photons, one can infer, and this resembles the Drake equation, because you have a lot of parameters there. But we could go through each of these parameters, and if one puts very conservative numbers, one finds that actually for fiducial values of the model parameters here, the accreting black hole emits a total number of ionizing photons that is comparable to that of its progenitor star. You know, you have to put numbers here, the number of photons that a star, massive star of population 3 would produce. This is the mass of the black hole over the mass of the star. The Eddington rate is just 10%. This is very, very conservative. We know that these ultraluminous X-ray sources are super Eddington. We put just 0.1 there. The accretion rate is, well, the age of the donor star. The energy distribution in the spectrum of the microquasar, the escape fraction, and from black hole and from the star. And the point is that the star will produce UVs, and the mean free path of UVs is much smaller than the mean free path of X-rays from the accreting black hole. So the X-rays from the accreting black hole can penetrate on the intergalactic medium much further than the UVs coming from the progenitor star. So the progenitor star will ionize up to a Stromer's sphere. But the whole intergalactic medium is neutral. So you have to reionize, heat and reionize the whole intergalactic medium. And furthermore, X-rays produce a large number of secondary ionizations. For a typical X-ray of 1 kV, you can produce 25 additional ionizations. So these accreting black holes are very efficient in producing ionization and heating the intergalactic medium. So as you know, with SKA and other projects, there is the intention of map in 3 dimensions how the reionization proceeded, and and this is the predictions from our models. You know that there is a correlation between the star formation rate, and the X-ray flux in galaxies. This is the group by Sunayev, is the Green, Ivanov, and Sunayev, given by this equation, and this Fx is a parameter that depends on the properties of the metallicity of the host galaxy, and what it is inferred is that this black hole, accreting black holes, would have heated the intergalactic medium up to temperatures that are at least 10,000 degrees. So heating the intergalactic medium over 10 to the 4 degrees Kelvin over large volumes may have prevented the formation of low-mass dwarf galaxies, because you need a certain mass to accrete gas from accrete matter from a warm gas. And one can calculate, we have calculated what would not form that early in the universe galaxies that had masses, or would have been very difficult to form galaxies with masses smaller than 10 to the 9 solar masses. I mean, this mass incorporates also, of course, dark matter. So these are, and so the conclusion is that the thermal history of the intergalactic medium, that where these black hole accreting sources had a direct impact on the properties of the faintest galaxies at high redshift and the smallest galaxies in the local universe. So on one hand, there is now the idea, the general idea, that black hole feedback had an important impact in galaxy formation and evolution. And as you know, there is the idea that jets, like in the case of the Perseus cluster, could have prevented the unlimited growth of massive galaxies. Namely, these galaxies accrete matter, but if you have a supermassive black hole, there is a limit. The black hole has a feedback that impedes the collapse of more matter and sets a limit to the mass of the galaxies, an upper limit. On the contrary, feedback from the first generations of these black hole high mass X-ray binaries heated and partially ionized the intergalactic medium, preventing the formation of very large numbers of dwarf galaxies with masses smaller than 10 to the 9 solar masses. So supermassive black holes set an upper limit for the mass of galaxies, and stellar mass black holes set a lower limit for the mass of dwarf galaxies. And this is, as you know, this might be important to account. This is a possibility to explain the problem that is a classical problem with the cold dark matter model that predicts an extremely large quantity of dwarf galaxies that we don't see. There are some possible explanations, but this is another one. And the question is, could feedback, namely radiation and jets from stellar black holes, reconcile the apparent discrepancy of the observations with the predictions of the cold dark matter model? Namely, the cold dark matter model explains the structure of the universe at large scales, but is failing to explain the structure of the universe at small scales. And one of the problems is the very large number of small mass dwarf galaxies in the local group of galaxies. And then supermassive black holes could perhaps also explain the absence of prominent cusps in the central bulges of galaxies. So this is an idea that we are proposing, and Nature, the editor of Nature was very interested in this, and I sent a couple of pages, and he said he wanted it. But because of CTA and other things, it took me 1 year to write this paper. And now he said, no, there is already another paper on the same subject, and although your idea is different, we don't publish two reviews on the same subject from 1 week to the next. So, in addition, there is a point that you rose when we talk in Paris, is whether could this large population of black hole binaries be important sources in the local universe for gravitational waves, namely because you have two black holes that if they form directly, they will remain gravitationally bound, and there will be a point where they merge and produce gravitational waves. But the question is whether those very early black hole binaries would have survived until the present epoch of the universe. So this is an open question. Okay, I think I have talked 50 minutes.
Questions to Dr.
Felix, if you are right, then in the early times of our galaxy, when the halo was forming, many black hole binaries could have been formed, and they should remain there. What about the microlensing studies? Have they revealed a population of black holes in the halo of our galaxy?
No. As you know, there was just one possible case. that from the micro lensing, but it's ambiguous if it is due to the fact that it's an object moving almost along the line of sight or not. But there is just one, and I haven't made the calculations whether we should have seen more events than this one that has been seen. I haven't done the calculations. And,
so if I understand correctly, for accounting for the reionization, it is proposed now that both those systems, I mean the black holes in binary systems, plus a population of binary massive stars, population 3, combined, and is very enough to provide them the number of dimensional photons. Is that true, or do you also need, for example, black holes, active galactic black holes for the realization?
Yes. Well, to reionize in the very early phases the universe, I would say that with massive stars, the progenitors of black holes, and also the black hole binaries, that will be enough. But then to sustain the ionization of the intergalactic medium, very likely you need AGNs. But the AGN epoch apparently came later. I mean, the furthest AGN detected so far is at 6.7, I think. And whereas galaxies now are being detected up to 8 and something, even 9, reaching of 9. So galaxies, stars, and the fossils, the black holes, stellar mass black holes, should have acted before the AGN.
And what about the initial mass function for this first object? Were normal, or do you need special?
We use saltpeter, but very likely is not saltpeter. I mean, there is a
more
upper mass cutoff in the IMF. But well, this is one of the parameters that are there in this sort of Drake equation. I mean, that you can play with it.
I have a couple of questions. The first one is about the time scale for the formation of the disk that you need to feed the black hole in order the black hole to show up. In particular, these early black holes, is the time scale enough to create the accretion disk?
Well, yes.
Or in other words, I mean, you have this implosion, you create this black hole, and then you have to, from whatever is there, you have to create an accretion disk for the whole thing to be bright. What are the time scales for this process?
Well, they can be formed very rapidly because the donor star is a massive star. And first you have feeding by the wind of the massive star, and also form, like in Cygnus X1, a disk. So you have the two processes, and it's very rapid. I mean, the donor star is there. I mean, it's providing the mass.
Okay, may I? Okay, and another question is about if the explosion, I mean, the photons that are created by these black holes are quenching the formation of low mass galaxies. I mean, these high mass stars that are the progenitors of the black holes, they probably have metallicities which are non-solar, so to say, or alpha enhanced or something like that. And so they should, one should be able to see the fingerprints of this strange way of creating metals in these low mass galaxies. Do you know whether there are predictions for that, and whether these low mass galaxies do show this strange behavior? Because, I mean, alpha enhancing, well, Do you know whether that there are predictions and whether they are confirmed?
Yes. Yes. See, I mean, if some of these stars, this is the production. I mean, for stars, the prediction is for stars with masses, progenitors, in between 140 and 200 solar masses. By pair instability, the star explodes. I mean, it disappears. And you could pollute the interstellar medium with those heavy elements very rapidly. And, well, this is an idea. We don't know if this takes place, but it's a prediction. If you can form stars with masses greater than 140 solar masses in this range, the star doesn't collapse neither into a black hole or neutron star. Just it disappears. It explodes and sheds all the matter into the intergalactic medium.
These metals have been observed in these low mass galaxies.
Well, there is no. This low mass, these very far away galaxies at reaches of 8, 7, and 8 is very difficult to do spectroscopy. There is just one where it has been claimed.
I'm thinking about nearby galaxies.
Yes, there is a claim that in one gamma ray burst was produced by this type of phenomenon of pair instability. There is an article in Nature about that. Yes. So this is a possibility. I don't believe too much in that article, but it has been proposed.
Above these masses again implodes.
Okay. Yes.
A couple more questions? No. Okay, so let's thank the speaker.
Okay. Thank you very much.